gas chromatography-mass spectrometry, and liquid chromatography-mass spectrometry. These two systems represent the most significant investments in any modern analytical chemistry lab, but picking the wrong instrument for your sample has immediate consequences. Choose the wrong machine, and you risk destroying fragile, irreplaceable evidence in a blast of intense glowing heat. Make the opposite mistake, and your target chemical simply vanishes into background noise because the extraction method wasn't compatible with the chemistry. The decision depends entirely on the physical nature of your sample. If you're handed an unknown synthetic powder from a drug seizure, you're dealing with compounds that are often fragile and easily degraded. But if you're investigating charred debris from an arson scene, you need to find resilient, highly volatile accelerants like gasoline or kerosene. To analyze these substances, you have to subject them to physical extremes, either baking them at 250 degrees Celsius or squeezing them through microcolumns at 15,000 psi. The choice isn't about which machine is better overall. It's about which set of physical conditions mathematically aligns with your sample's ability to survive the trip to the detector. Let's start with gas chromatography-Mass Spectrometry, or GCMS. For this machine to work, your sample must be volatile. It has to be able to turn into a gas. The liquid sample enters an injection port heated to 320 degrees Celsius, flash vaporizing into a gas immediately. Next, during electron impact ionization, molecules are struck by a 70 electron-volt beam, violently shattering into specific, smaller fragment pieces. Because this impact is so aggressive and standardized, a specific molecule will break apart in the exact same way every single time. It creates a predictable, uniform fingerprint. This uniformity is what allows for global library matching. A spectrum you generate today can be matched against the NIST database with mathematical certainty because the fragmentation rules are the same in every lab. But this process has a strict limit. Generally, only small molecules, those under 800 Daltons, can survive this heat and impact without completely falling apart. GCMS essentially trades the survival of large molecules for a definitive identification that is recognized by courts and databases worldwide. That brings us to the weaknesses. Because GCMS relies on internal vacuums and dry gas streams, it cannot handle water. This means you can't directly inject biological fluids, like blood or urine. The water would ruin the column and the vacuum. To get around this, technicians have to perform slow, manual extractions. They must chemically force these biological samples to become volatile before they can even be injected. Then there is the heat. If your target compound is heat sensitive, it will decompose into useless carbon soot inside the injection port before the machine ever has a chance to analyze it. If your lab's workload is mostly biological fluids or fragile molecules, GCMS will often destroy your evidence before it can provide an answer. This is where liquid chromatography-mass spectrometry, or LCMS, excels. It is designed to analyze fragile molecules at ambient temperatures. Instead of heat, it uses pressure. It forces liquid solvents through microcolumns at up to 15,000 psi to separate the compounds. This liquid path allows the machine to carry massive compounds, like 100,000 Dalton proteins, through the system while keeping them entirely intact. To move these molecules into the mass spectrometer, the system uses Electrospray ionization. As you can see in this Taylor cone diagram, a high-voltage spray releases the whole molecules into the gas phase without shattering them. This soft ionization preserves the sample, but it comes with a trade-off. Fragmentation patterns in LCMS vary depending on the mobile phase, the voltage, and even the manufacturer of the machine. Because of that variability, there is no universal, standardized NIST library for LCMS. You can't simply hit a search button to identify an unknown compound with the same certainty as GCMS. LCMS trades that universal library matching for the ability to analyze complex biological samples that would otherwise be destroyed by heat. To make up for the lack of a universal library, labs use Tandem mass spectrometry, or LCMS-MS, for highly targeted analysis. This diagram shows selected reaction monitoring. The machine filters a specific precursor ion in the first stage, breaks it in the second, and measures a specific fragment in the third. This multi-stage filtering effectively ignores all the chemical noise from a messy biological sample, focusing only on the target. This results in extreme sensitivity. LCMS-MS can detect specific drugs at concentrations as low as a femtogram. That's 1/4,000th of a gram. Since LCMS works with liquids, toxicologists can often inject biological extracts directly into the machine, significantly reducing the labor required for sample preparation. When you need to find trace amounts of a known drug or metabolite in a biological fluid, LCMS-MS is the most effective tool available. Ultimately, the decision comes down to matching your sample's physical properties to the data you need. This flowchart illustrates the path. For small, volatile, and nonpolar unknowns, GCMS is the standard choice. It is the only option when you require a standardized library match to prove a compound's identity in a forensic or environmental investigation. But for heat-sensitive or liquid-based samples, like proteins and drug metabolites, the path leads directly to LCMS. This is the preferred route for clinical toxicology and pharmaceutical research, where finding trace amounts of a specific compound is more important than blind searches. Because they are governed by different physical laws regarding heat and pressure, one machine cannot truly replace the other. A fully equipped lab utilizes both systems to ensure that every sample, whether it's a volatile solvent from a fire or a trace protein from a blood vial, can be identified with total certainty and precision.